Hey everyone, welcome back to Chem Story. In this lesson, we're going to talk about how to systematically draw chemical structures. It doesn't matter whether the molecule has only single bonds, or includes double, or even triple bonds. We'll go through a clear, step-by-step process to make sure we're building the most accurate and stable structure possible. By using this method, you'll be able to make sure that every atom follows the octet rule, formal charges are minimized, and the overall structure actually makes sense. As we go through this, we'll also talk about some key concepts, like valence electrons, common bonding patterns, and how to adjust for formal charges. These ideas will really help you draw chemical structures with more confidence. All right, let's get into it. Before we dive into the details, let's take a quick step back and look at the bigger picture. The very first thing we do is arrange the atoms and connect them using single bonds based on the molecular formula we're given. If the structure is more complex, we can use a few general rules to help figure out the best layout. Once that's done, we check if each atom has the expected number of bonds, and that depends on the number of valence electrons. Remember, the number of bonds an atom typically forms is determined by how many unpaired valence electrons it has. As we go through this step, it's helpful to keep track of the total valence electron count, because we'll need that later when we calculate formal charges. If an atom doesn't have enough bonds, we'll add double or triple bonds as needed to balance things out. But if every atom already has the number of bonds it's supposed to, we can skip that and move straight to adding lone pairs. Now we add lone pairs to each atom based on what the octet rule tells us they need. And if the structure is fine with just single bonds, then once the lone pairs are in place, we're basically done. But if an atom still doesn't satisfy the octet rule, we might need to convert some lone pairs into bonding pairs to make those final adjustments. Last but not least, we go back and review everything, make sure the formal charges are correct, and check that the structure we've drawn is as stable as possible. All right, now let's go through each of these steps using diazomethane, Ch.02, and methyl isocyanide, Ch3NC, as our examples. First, we need to figure out where each atom should go in the structure. Most of the time, we can figure this out just by looking at the molecular formula. But when we're dealing with more complex molecules, there are a few general rules that help us make the right call. A great place to start is by identifying the least electronegative atom, except for hydrogen. That atom usually goes in the center of the structure because it can form more bonds compared to the others. In most cases, carbon is the best candidate for the central atom. If there's no carbon, nitrogen is often next in line. And after that, oxygen can sometimes play that role too. On the other hand, hydrogen and halogens, like fluorine or chlorine, can only form one bond, so they always stay on the outside edges of the structure, never in the center. Let's take diazomethane as an example. Here, the best choice for the central atom is carbon. Hydrogen can only form one bond, so we place the two hydrogen atoms on the carbon. Now, we need to connect the two nitrogen atoms, but instead of attaching both nitrogens directly to the carbon, only the first nitrogen is bonded to carbon. Then, the second nitrogen is connected to that first nitrogen, so the basic structure looks like this: H2C, NN. Carbon in the center, bonded to two hydrogens and one nitrogen, and then that nitrogen is bonded to another nitrogen. Now let's look at methyl isocyanide. We'll start by placing a carbon atom, let's call it C1, at the center. Then we attach three hydrogen atoms to C1, just like we would for a methyl group. Next, we bond a nitrogen atom to that central carbon. And finally, we connect another carbon atom, which we'll call C2, to the nitrogen. So our initial structure looks like this: CH3NC. Now, let's check if each atom has the right number of bonds, based on its valence electrons. Atoms form bonds depending on how many unpaired valence electrons they have. For example, carbon has a total of 4 valence electrons, and since all 4 are unpaired, it can form 4 bonds, which gives it a stable structure. Nitrogen has 5 valence electrons, but only 3 of them are unpaired, so it usually forms 3 bonds, while the remaining 2 paired electrons stay as a lone pair. Oxygen has 6 valence electrons with 2 unpaired electrons, so it typically forms 2 bonds, and the other 4 electrons remain as 2 lone pairs. Hydrogen and halogens each have just 1 unpaired electron, so they can only form a single bond, nothing more. Understanding these bonding patterns is really important, because valence electrons don't just determine bonding, they also play a big role when we calculate formal charges. Since we'll be using this information later, make sure to keep these values in mind as we go. Now, if all the atoms in your structure already have the right number of bonds, you can skip step 3 and go straight to step 4. All right, let's go back and review our structures. Let's take a closer look at the atoms in diazomethane. Right now, carbon is forming 3 bonds, but since carbon usually forms 4, it still needs one more bond to be complete. The middle nitrogen, let's call it N1, is forming 2 bonds, but nitrogen typically forms 3, so this atom also needs one more bond. Now for the terminal nitrogen, or N2. It currently has only one bond. And because nitrogen likes to have 3 bonds, this atom still needs 2 more to reach a stable configuration. Now let's check the atoms in methyl isocyanide. The first carbon, C1, already has 4 bonds, so it's completely stable. No changes needed there. The nitrogen atom in the middle is forming 2 bonds right now, but since nitrogen typically wants 3, it still needs one more bond to be satisfied. As for the terminal carbon, C2, it only has 1 bond at the moment. But remember, carbon prefers to have 4 bonds, so this one still needs 3 more to complete its structure. If an atom doesn't have enough bonds, we need to add pi bonds to fix the issue. And here's the key rule. The number of bonds we add should be based on the atom that needs the fewest extra bonds. So for example, if one atom is missing 3 bonds and another is missing just 1, we don't just go ahead and add 3 bonds. Instead, we only add 1 bond, enough to satisfy the atom that's closest to being complete. That way, we're making the smallest possible adjustment to stabilize the structure. Now, if there are multiple places where we could add that extra bond, we give priority to the location where carbon can reach its full 4 bonds. Unlike other heteroatoms that can hold on to lone pairs, carbon doesn't like having lone pairs. It much prefers to form more bonds and satisfy its valency that way. So when we're deciding where to place that extra bond, we adjust the structure to make sure that carbon gets its full 4 bonds whenever possible. By following these rules, we can make sure that every atom ends up with the correct number of bonds, and the overall structure stays as stable as possible. Let's go back to diazomethane and make the necessary adjustments so that every atom has the correct number of bonds. Right now, carbon is missing 1 bond, and the middle nitrogen N1 also needs 1 more bond to reach its preferred state. To fix that, we can add a pi bond between carbon and N1. That gives us this updated structure, H2C double bond NN. Now, both carbon and N1 have the number of bonds they need. Now for methyl isocyanide. In this case, nitrogen is missing 1 bond, while the terminal carbon, C2, still needs 3 more bonds. Since nitrogen is the one that needs fewer additional bonds, we'll add a pi bond between nitrogen and C2. That gives us the updated structure, CH3, N double bond C. With this change, nitrogen now has 3 bonds, and C2 is 1 step closer to reaching 4. Now we're at the step where we figure out how many electrons are missing and start placing the lone pairs. To do that, we can use a simple formula. This helps us determine how many lone pairs each atom should have by looking at its valence electrons, formal charge, and bonding electrons. Here's how it works. First, we start with the number of valence electrons the atom would have in its neutral state. Then we subtract the formal charge, and most of the time, we assume that's 0. Next, we subtract half of the bonding electrons. That gives us the number of electrons left for that atom. And finally, we divide that number by 2, which tells us how many lone pairs we need to add. All right, let's go ahead and calculate how many lone pairs each atom in diazomethane needs. Using the formula we just talked about, we find that the middle nitrogen N1 needs 1 lone pair. The terminal nitrogen N2 needs a bit more. It requires 2 lone pairs. All right, now let's figure out how many lone pairs each atom in methyl isocyanide needs. Using the same formula, we find that the nitrogen needs 1 lone pair, and the terminal carbon C2 also needs 1 lone pair. Once we place those lone pairs, in most cases, the molecular structure is complete. But if any atoms still don't satisfy the octet rule, we'll move on to step 5 and make the necessary adjustments. Alright, now let's make the final adjustments to make sure that as many atoms as possible satisfy the octet rule. Sometimes, even after we've placed all the lone pairs, a few atoms still might not have a complete octet. When that happens, we need to fix it by moving a lone pair from a neighboring atom and turning it into a bond. Now, doing this might create formal charges, but here's the key point. Making sure atoms follow the octet rule is usually more important than keeping formal charges at 0. So when you're finalizing the structure, prioritize completing the octet, even if that means introducing a formal charge somewhere. By taking this step, we help the molecule reach its most stable form, where as many atoms as possible have a full set of valence electrons. In diazomethane, the terminal nitrogen N2 still doesn't have a full octet. To fix that, we take one of the lone pairs from the middle nitrogen N1 and convert it into an extra bond between the two nitrogens. That gives us an N double bond N, which helps N2 complete its octet. In methyl isocyanide, the terminal carbon C2 still doesn't satisfy the octet rule. To fix that, we take a lone pair from the nitrogen and turn it into an extra bond, giving us an N triple bond C. Next, let's double-check the formal charges. In diazomethane, N1 has a +1 charge, and N2 has a -1 charge. But since all atoms satisfy the octet rule, this is still the most stable form of the molecule. In methyl isocyanide, the nitrogen has a +1 formal charge, and the terminal carbon has a -1 charge. Even with these charges, the structure is stable because the octet rule is fully satisfied. And since both molecules have an overall charge of 0, they're neutral and exist in their most stable forms. And that's it. By following these steps, you can systematically build chemical structures while making sure everything is stable and all the electrons are correctly distributed. That wraps up today's lesson. Hope this breakdown helped you get a clear picture of how to draw molecular structures with confidence. Keep practicing, and pretty soon, this whole process will feel like second nature. If you have any questions, feel free to ask. Thanks for listening, and I'll see you next time.